Good morning, everyone. It's been a pleasure to be here in the city of Jaipur, the Pink City. Special thanks to Rakesh for organizing this, getting all of us together, 2, 3 days, nice meeting. So, what I'm going to talk about is mainly topology and applications of topology in condensed matter physics. And I'll progressively consider many of the aspects that are being applied on the topological matter. And one of them, Rajiv was saying yesterday that it made headlines about fault-tolerant quantum computations using Myra. And I'll not get into that, but I'll sort of be in the periphery of all of these. So given the name tweaking topological matter, so we'll tweak the topological systems in a certain way to make them having richer impacts and so on. Okay, so topology will get enhanced, will have enhanced features and many other things that will come along the way. So this is a brief content introduction to the content. So we'll talk about a little bit about topology. We'll talk about non-Hermitian systems, which are becoming very important because the Hermitian systems do not take into account the connection to the environment and the dissipation that is evident in all systems. We'll talk about periodically driven systems. So this is one of the tweaking of making a topological system non-Hermitian, driving the topological system using these periodic drives. We'll talk about crystalline topology, or what happens when you take into account crystallinity of these this crystal system or crystal lattices, the crystal properties. It gives rise to higher order topology. And finally, we'll have some applications in the tight binding model. And one of the things that I've chosen is a ladder compound. It's called a Creutz's ladder, and there's a reason behind choosing that. There are a lot of other things that we have done along these lines, but I'll not talk about that, and there'll be a short summary. But I start in a slightly different note, and let's talk about what people have been interested in for a very long time, maybe around 100 years or more than that. And one of the problems that have kept people busy till even 2003, 4, 5, around that is the thing called superconductivity. And it's important to look at the periodic table for every condensed matter person to understand that what these are. And if you look at this part is all magnets. And some of these parts are the superconductors. So the superconductors and the magnets are actually two sides of the same coin. And one has larger correlation between the electrons, and one has smaller correlation between the electrons. The overlap of the electronic wave functions are limited in the magnets, and they are larger in superconductors. I mean, don't take this whole area to be literally. I mean, they just wanted to make sure that there's some superconductors here, but mostly these are magnets. And some elementary superconductive, the early superconductors, their TCs are recorded, and some of them have very low TCs, and some of the TCs. And till about 1950s, the highest TC, the transition temperature, which demarcates superconductor and a metallic phase, was found to be around 23 Kelvin. So that was this compound superconductor called the Nb3G, niobium germanium. So in 1957, these three wonderful gentlemen, Bardeen, Cooper, and Schiffer, it's actually Cooper's work. Cooper was a PhD student, Leo Cooper. And this Schiffer was his supervisor, and Bardeen was the department chair. So they wrote down this theory of superconductivity. It's one of the finest, and at that time it was a very nice microscopic theory that emerged. And there was why the theory was so successful in explaining all these earlier superconductors is that it has a variational theory, and it had just one fitting parameter, and you could get the TC, you could get the Meissner effect, which is expulsion of the magnetic field, and so on. So this picture that you see on the right is actually a Schiffer's demonstration of Cooper pairs. So in a room, there are these dancing rooms, and then there are equal number of male and female partners. And by some means, they all find a partner with each other. That's one male and one sitting. On this, Bogolyubov was in a different way. I mean, Bogolyubov theory or doing that transformation.
No, before that, before these people, he had this from what I understand.
No, Bogolyubov had a transformation where a mean.
That was that doesn't know that. Well, okay. The point, the Russians tell me.
Okay.
Bogolyubov published this research.
Okay. Before. Okay. That could be possible. Yeah. So what happens? What is this saying is that so each one of them find a partner, and once they find a partner, they start dancing together throughout the room, making no collisions with each other. So these are the Cooper pairs, and what forms a glue between the Cooper pairs are the lattice excitations or the phonons. So so this was nicely described that when a horse moves through a dusty field, it picks up a lot of dust, so you don't see the horse, you see there's a ball of dust drifting. So when an electron moves in an ionic background, it picks up a lot of positive charges. So another electron doesn't see that electron, but it sees a cloud of positive charge and gets attracted and forms a pair. So that's the Cooper pair. So once they form a pair, they are like quasi-particles, or they become like free particles, and they move around, dance around the whole room without colliding into each other, giving rise to a supercurrent. And this was very nice, and it was successful in sort of explaining superconductivity. And then what happened is that as the time progressed, this year was this liquefaction of helium, and so mercury was found superconducting by Kamerlingh Owens. And then there was this theory of BCS, and then suddenly around 1986, NB3 GE was around 1978 or so, and then suddenly it shot up to as much as 160, 65 Kelvin, and so on and so forth. And then there are these arsenides, and there are lanthanides, and various kinds of superconductors that were discovered later and went on, pressure-induced superconductivity in hydrides and so on. Something that happened here was taken people by surprise, because they couldn't formulate anything. They couldn't have a theory. They couldn't, write down a Hamiltonian for that. And the reason is this thing. This was discovered by these two gentlemen called Bednorz and Muller, and there's this IBM Zurich lab in Switzerland, and they got a superconductor which is a strontium cuprate, lanthanum strontium cuprate, and the TC was at that time about 36 Kelvin. Okay, so that was a jump that they had, and then it just went on and on. The reason that it never got solved and it was dumped after maybe 20 years of research is this greenish region, which made people discard all the theories, because you should know what's the metallic state, and if you don't know what the metallic state, then you don't know what the starting point is, and if you don't know the starting point, no theory can ever get see the light of the day. And so this is a strange metal, which means it's not a Fermi liquid. And if it's not a Fermi liquid, you don't know what at this optimal doping or at lower doping, what kind of phase is it. So there was very difficult to write down a theory for that. At the overdoped region, it's more or less a Fermi liquid. So there's a crossover line that are being indicated here. And then there are this pseudo gap region where there are gaps. The Cooper pairs are phase. They have the same amplitude, but they are probably not phase coherent, and so on and so forth. There's a temperature versus this doping, which was one of the hole doping or electron doping. Here we are talking about hole doping. And this blue dome is actually the superconducting dome. There's another important thing here is that this blue dome is very close to an antiferromagnetic insulator. So there's an insulating phase, and then there's a superconducting phase, which are here there's some kind of a glassy phase which never got really worked out that what kind of phase is this. So then coming to a bit of magnetism, I'll not spend. Yeah, it's all experiment based. Yes, yes.
So how does one assign the properties that you have ascribed to different parts of the diagram?
So basic.
Are only coming from the experimental side. How do you find?
Absolutely. So what you see is that if you start heating up the thing and calculate various coefficients, that how the say the chi or the susceptibility go as a function of temperature, or how the specific heat goes as a function of temperature, then the kind of T minus Tc or T to the power alpha. So the alpha that you get from Fermi liquid theory is not there here or here. Okay, so these are the experimental signals.
People have some precise understanding of what is a strange metal, or whatever is not a Fermi liquid and is not a pseudo gap is just called a Fermi. It's called a strange metal.
It's called a strange metal. It's not a non-Fermi liquid. Yeah. Coming to a little bit of magnetism, I'll not spend more time on that, but this is also equally complicated problem. There are too many terms there. You have a term which is called as the exchange energy, which is the Heisenberg exchange, JSI dot Sj, most of you are familiar with. The uniaxial anisotropy, then there's something called a Zylestinski-Moria interaction, and so on and so forth, and there are dipolar interaction, etc. So Hamiltonian having so many terms that are there here, it became very difficult to solve in a closed form. There are only certain approximations that you can use, or you can do some transformations. These are called a Holstein-Primakov transformation, which basically does a linear spin wave theory and converts the spin operator into boson operators, and then write it down, this Hamiltonian, in terms of these A dagger operators, and then it becomes a non-interacting bosonic problem. In some magnon basis, you're creating a magnon here by this S minus, creating two magnons in the at the near vicinity, maybe Ri and Ri plus some delta, and so on. And then you do this, then you apply it to this Hamiltonian and write it in this A dagger basis, and then it becomes solvable in some cases where if the linear spin wave theory works, and so on.
Just one minor quick question about
Yeah.
this. So you said something very quickly about bosonization happening. Can you elaborate on that a little bit here?
Here, yeah.
Wherever it is happening.
Yeah, so you you look at this Hamiltonian and see that it becomes hopeless for you not to be able to solve it, because there are these terms which are S cross S, and there are S dot S, and so on and so forth. So you think about how to solve it, and what you do is that you introduce this concept of magnons. Magnons are nothing but the spin waves. And when you do that, so if you write it down in this S minus, and S minus is going to lower a spin at the site Ri on an ordered state. So the zero is the ordered state. Okay, some kind of either if it's a ferromagnet, then it's a Curie state, and if it's an antiferromagnet, it's a Neal state. And then you make these transformations, this Si minus and at another site Sj minus, in terms of these operators, A, B operators, and so on, and then you put it back into this. Now it looks solvable, and it looks like a non-interacting problem.
And
It's a bosonized problem. And why are these good? Because they conform to this commutation relations of both spins and bosons. These are canonical transformations. It doesn't matter, actually. It doesn't matter. Yeah, we do it in 2 dimensions, but it doesn't matter.
You're saying you always have terms like either And two spin halves looks like a boson. Is that what you're saying?
You have to look at this kind of transformation. It's not two spin halves, but a spin lowering or a spin raising is looked upon either creating, so spin lowering is like creating a boson and spin raising is like annihilating a boson, and the Z component looks like this A dagger A, which is like a number operator for the bosons. Yeah, okay.
Maybe just to paraphrase that for everybody, basically, you're looking at two spin half or half integer spin states, and a transition between them is integer spin, and that's the boson.
Okay, yeah, okay, yeah. So now all these things were becoming very important, and it's around 2016 this topology in the field of condensed matter made an entry in a somewhat interesting way, and this is the topology in condensed matter that I'm going to talk about. And everything started with this example of, or rather this quantum Hall effect, which was reckoned to be the first topological state or the topological state of matter. And what you see in green is the Hall conductivity or the Hall resistivity here. So these are shown in green, and what you see in red is the longitudinal conductivity. So if you remember the Hall effect experiment, so you have a two-dimensional sample, which is usually a semiconductor, and then you have perpendicular magnetic field, and then you have a longitudinal current that flows in a certain direction. And then you measure the voltage at the other transverse direction, and this is what you get if you can access a magnetic field from 0 to 15 Tesla. And why Edwin Hall missed it is that Edwin Hall was right here all the time, because in those days getting big electromagnet was not possible, and he could pretty much in the millitesla regime that. So you see what we do in the lab, the undergraduate lab, is precisely this small green part, and we miss all of the interesting physics that is there at larger magnetic field. And these plateaus, they are at h over e square with a precision of 10 to the power minus 8. Okay, so this h over e square is 25.8 kilo ohms. So this experiment done on MOSFETs by von Klitzing, and it could give you the unit of resistance to be with a precision of 10 to the power minus 8 was a real surprise. I mean, this metrology has never seen in such lab experiments done in presence of magnetic field, and these MOSFETs have a lot of defects and inhomogeneities and so on. So it's just a dirty lab experiment could produce these invariants. Later on, there are 4 people called, say it again? Yes, low temperature is needed, but it's not that important. I mean, when you have very large magnetic field, then it's not needed. This was the discovery in 1980 by Klitzing, and got a Nobel Prize in 1985. So it was transport properties of silicon MOSFETs and large low T and large B in Grenoble. And these Hall effect, the Hall plateaus were seen as dissipation-less states. And if you look at it, these are the longitudinal plateaus, and which shows that they are undergoing series of transitions from a metallic state to a insulating state, and back to a metallic state, back to an insulating state. So wherever there is a jump in the resistivity, that's an insulating state, and when there is no resistivity, that's a metallic state. So metal insulator transition, and no other system shows. Of course, there's a feature of a 2D system in presence of a strong magnetic field. So this was called as the IQHE, or the integer quantum Hall effect, where these plateaus were seen at integer values of h over e square. Soon these 3 gentlemen, Dan Swee, Stormer, and Bob Laughlin, they discovered that in addition to that, you can't see it very well, but these are plateaus seen at all kinds of fractions, mainly rational fractions with the integer, with the denominator to be larger than the numerator, but also at other fractions. And these are seen because of, so why this is seen is that you have these Landau levels formed for the electrons, the charged particles in a magnetic field, and these Landau levels get broadened because of the disorder. So as if you fix your chemical potential at a site and progressively tune on the magnetic field, just like what was done in that experiment, then the Fermi level will come sometimes in the Landau band, and when it gets even bigger, it can go out of the Landau band. So when you are inside the Landau band, you will have conduction, so your resistivity will freeze. And then when you do not have conduction and you are outside the Landau band, or your this thing is the chemical potential is outside the Landau band, you will have so there's a jump in the resistivity. That's what was shown. But then it turned out that at cleaner samples, so there's a hierarchy of energy that is important here, as a disorder energy, magnetic energy, and of course the energy associated, basically the disorder and the magnetic field energy or the cyclotron energy. So if you make the samples cleaner and cleaner, and that's what has happened between 80 to 82, that they had gotten cleaner samples, and then you see that there are gaps that open up inside the Landau band as well, and if the chemical potential happen to be that in that gap, you actually get a plateau at some fractional. These are all odd denominators and can only be explained by Laughlin wave function, but there are also even denominators which cannot be explained by Laughlin wave functions.
Have they been found?
Yeah, they have been found. They have been found, and they are actually the excited states of matter. In fact, the excited states will have these Majorana fermions and things like that, the excitations. So in the ground state, there is nothing. So Laughlin wave function. So Laughlin couldn't solve this problem because it's an interacting problem, many body problem. So what great people do is that when they can't solve a problem, they just write down the solution. And Laughlin wrote down the solution as a variational state. And it's so good that if you do, say, 10 or 15 electrons and take a Coulomb interaction between the electrons and do a exact diagonalization of the problem, the match of the energy with the variational energy of Laughlin is 99.9%. Okay, so the really Laughlin was able to solve this problem, and then Jain came and made it more interesting, and he proposed this composite fermions and so on, and which of course had its effect there. So coming back, so this is a quantum Hall state where you have these cyclotron orbits in the insulating, in the bulk of the material, and at the edges you have this transmission where these electrons cannot complete the orbits, and they will propagate in this along the edges. So this was the name topological insulator, because it's insulating at the bulk, if there is no drift, and it is conducting at the edges. Okay. So then, of course, this 2016 came, and these three gentlemen again sort of changed the scenario, in which David Thouless got a Nobel Prize with a share of half, because it says that topological matter and topological phase transitions, Duncan Haldane and Michael Kosteles, they shared a prize share of 1/4 each, because they were awarded for the topology of matter. Yeah.
Insulating in the bulk and conducting at the edges, is this somewhere related to the skin effect, or
No, they're not skin effect. I'll come to skin effect. Yeah. This was a paper that Haldane wrote in 1988, and very strange paper. Graphene was discovered in 2004, but before that, people knew about graphene. So graphene has a honeycomb structure, and it's an interesting thing by itself, because if you look at graphene, properties of graphene, you can hold a graphene in your hand and if you stretch it, it will probably stretch an entire football field. So the expansibility is huge. And then there are a lot of a lot of applications of graphene and so on and so forth. But this was graphene really. It was this thing that was done on graphene, and he wanted to show that look, a magnetic field is not necessary for Hall effect, which is what I have been talking about. And he came and dropped a bomb saying that you need to simply break the time reversal symmetry of a given system. And the way he did it is that he introduced a second neighbor complex hopping in a honeycomb lattice. So honeycomb is actually is a bipartite lattice formed of two A and B units, two atoms. In graphene, these two atoms are identical, both are carbon atoms, but nevertheless it's bipartite. So it's A to A or B to B hopping is complex, and it's chiral. So it means that it is having a plus sign if you go clockwise and a minus sign if you go anti-clockwise. If you do that, it is equivalent to breaking the time reversal symmetry. So for getting a Hall effect, you don't need a magnetic field. You just need to break the time reversal symmetry, and magnetic field anyway does break time reversal symmetry, which was there in the experiment. So this was one of the developments, and this is called as a Halden model. So coming back to this topology issue and so on. So this is this thing is knotted in a particular way. So this is topological, and if you need to get into from here to here, you need to cut it open. And this is a topologically trivial. And what are these? These are nothing but the wave functions. We are showing the wave functions. So how the wave functions are knotted. So if you have a system, look at the wave functions, and the knotting of the wave functions will tell you whether it's a topologically trivial or a topologically non-trivial. That is, whether it's a topological object or topological system and so on. It, of course, is a branch of mathematics that it studies the properties which are invariant under smooth deformation. So if I draw a triangle and a square and a circle, you would, of course, say that these are three different geometric shapes, but they are topologically same because they all are closed figures. Okay, so the topology is not. So if you want to know in very simple language that what is topology, is the integral of a geometric quantity, and I'll show that. So very familiar to everybody, and this is that mug becoming a donut. And what it really means is that there's a smooth deformation where the mug becomes a donut, which means the mug and the donut, they belong to the same topology class. And if you want to know what it means in condensed matter physics, it means that if you tweak a Hamiltonian, if you change a Hamiltonian or tune a Hamiltonian, the number of states that you have below the Fermi level, they would not change. And that's what this smooth deformation means. The word smooth means there is certain things that will remain invariant. And in this case, the things that remain invariant are the number of energy levels below the Fermi level. So this is what this smooth deformation really means. So you deform the Hamiltonian, and this is what happens. So this is, we have already shown that these are cyclotron orbits and so on. And if you want to look at it in the K space, E versus K, you have a bulk gap. The conduction band and the valence band have a clear gap. But there are, edge modes that will traverse across the Fermi level in a topological insulator, and these green lines would not be there in a trivial insulator. And the topological insulator will have some energy modes, propagating across the Fermi level, and will propagate from the conduction to the valence band. So clearly, these topological insulators are distinct than normal insulators, which are also called as a band insulators. And so this is one way of looking at it, that there is a band inversion. So in a normal insulator, you have p orbitals in the valence band and you have s orbitals in the conduction band. And if the normal insulator there's a gap there. If the normal insulator actually undergoes a transformation to a topological insulator, you'll see that some of the S here will become P, and some of the P will become S, and this is called as a band inversion. So if there is a band inversion that occurs from from the conduction in the process of tuning the Hamiltonian, then the Hamiltonian is has a topological phase transition, and this is kind of topological. It's a Mobius strip. So this Mobius strip has, these are s orbitals, and then there are p orbitals at the this thing at the outer this thing, and so on and so forth. So there are these similar things that are being told here, that these are basically emphasizing the difference between the band insulators, normal insulators, and topological insulators. So what are topological insulators? And one of the things that people jumped up when they saw this model of a polyacetylene, long chain polyacetylene molecule, where there are these carbon, you see this carbon which is connected to by a single bond to a hydrogen, each carbon. But the carbon, there is a double bond here, there is a single bond, there is a double, there is a single. So that's the model for a polyacetylene molecule. Assumably, this is an organic molecule and which has some conductivity and so on and so forth. But the condensed matter people found it very interesting that if you write down only the Hamiltonian for these carbon atoms and take it as a dimer, that is, this hopping or the kinetic energy is T1 and this kinetic energy is T2, or U and V, or V and W, different things that people talk about. Then whether T1 is greater than T2 or T2 is greater than T1, you'll have a topological state that emerges. And how do we know that there's a topological state that emerges? I'll tell you that. And in 1D, so that's the sort of scenario that you'll have at the edges, there'll be some zero modes and or conducting modes. Here, of course, there are insulating modes. And in 2D, there are these currents in the along the periphery. And in 3D, there are surface states which are there. So the bulk is insulating and the surface is conducting here. Here the bulk is insulating and the edges are conducting. Here the bulk is insulating and maybe the edges have some distinct properties. Okay. And so that brings us to an issue of bulk edge correspondence. So it tells you that it's very difficult to look at the edges per se separately. And if you do not want to look at the edges, how do you know what are the what are the properties of the edges? And importantly, when you have to look at the edges, you have to open the system. You can't talk about periodic boundary conditions and so on. But sometimes if the system has a translational invariance, you would want to talk about periodic boundary conditions. So this tells you that you don't really need to look at the surface, but from the bulk properties, you can calculate the surface or the edge properties. And this is called as a bulk edge correspondence. And this was given by these Thouless, Komoto, Nightingale, and Dennis, who have also conjectured that these plateaus that you see in the quantum Hall case are actually the topological invariants. Okay. And this is the way you calculate this. This is the Hall conductivity, and this is how you calculate the Hall conductivity, and is known as a TKNN invariant. TKNN goes by this four people's name. And what you actually do is that you integrate the Berry curvature over the entire Brillouin zone. Okay. So that brings us to this topological invariance. And if you really want to understand what these topological invariants are, let's look at this quantity called as a Gaussian curvature for 1 by R1, R2, where these are the three different things considered with these three different shapes. And if you consider these R1 and R2 are basically the radius of curvature at the two at wherever you want to consider. Say at the equator or at the middle point and so on. And if you take this quantity, that's a geometric quantity, and you take this geometric quantity and integrate over the whole surface of this quantities, then it would have been difficult to do this integral if it is a very odd shaped object. And fortunately in maths, there's something called as a Gauss-Bonnet theorem, which tells you that these integral over this entire surface area gives a constant which counts the number of holes. So there's a whole number of holes is equal to 1, there's number of holes is equal to 0, and so on and so forth. So this K is analogous to the Berry curvature, and these surface that you talk about is analogous to the Brillouin zone. So everything seemed to fall in place, and the connection between geometry or topology to condensed matter physics becomes very apparent through this through this description. And we just need to calculate the Berry curvature and integrate it over the entire Brillouin zone. If you get a number, finite number, then it's topologically non-trivial. If you get a number which is 0, then it's of course topologically trivial. Forget this. So if G is equal to 1, then of course you get it at 0. So for this particular case, you get a number which is equal to 0. But if it's if G equal to 0, you get a 4 pi, which makes sense because you're doing it on a surface. So the surface of a unit sphere is 4 pi. But if you have G equal to 2 and so on, you get some number which is positive, negative, doesn't matter. I mean, this is this integral is finite, is what I'm trying to say.
One is a classical and another is a quantum.
Yes, okay, that way, yeah. No, there's no violation. For G equal to 1, yeah, it just becomes equal to 0. I mean, for the TKNN, this thing is non-zero, and that's what has been shown here. I mean, for this particular case, this is non-zero. So, yeah, there's no violation. All right. So that people started recognizing that there are very nice symmetries of the problem which need to be taken into account. And just like when you have too much of information, you want to put it in the form of a table, or that's the easiest way to do that. I mean, represent that. And we've seen how nicely the periodic table, Mendeleev's periodic table, was nicely coined. And you go from left to right, you have larger ionic radii and so on and so forth, electronegativity. So these are done depending on the symmetries, and these symmetries, they fall into different classes. So if a model has time reversal symmetry and charge conjugation symmetry and these chiral symmetry in some sense, not in non-Hermitian systems, but in Hermitian systems, this chiral symmetry is equal to the product of the time reversal and charge conjugation. So having 1, -1, and 0 means that 1 means that there is a symmetry, -1 means there's an antisymmetry, and 0 means that there's no symmetry. The topological insulators have been classified into these 8 varieties, BD1, C1, rather 10 varieties, and so on. So BD1, C1, A1, D3, C2, A2, D, C, A3, and each one of them, according to their dimensionality, they are called the topological invariants have been coined, which are called as Z invariant and Z2 invariant, and so on. So what's a Z invariant? So your the Hall conductivity or the Hall resistivity is a Z invariant, which can take values 1, 2, 3, 4, any value, and Z2 invariant can take only values 0 and 1. Okay, so these are some of the things, and it's only Z and Z2, and these are the classifications. So if you know by looking at a Hamiltonian which all symmetries it has, you can put it in a different, in one of these different classes. And once you know how to put them in different classes, then you can, in which dimension you're talking about, you know what the topological invariant is or the property of the invariant is, and you go back and calculate the Berry curvature integrated over the Brillouin zone, and that will give you the invariant. And you'll know that whether the system as a function of some tuning parameter has undergone a transformation from a normal insulator to a topological insulator, or a topological insulator to another topological insulator having a different topological invariant value.
What would be the observation?
Observation, yeah. So if you think of this thing, that the something that comes up with a topological property, it'll have edge modes, conducting edge modes, and which can be actually detected in the STM measurements. Okay, so
How will it distinguish Z2 or Z or?
how to distinguish between Z2 and Z? Correct. So that, of course, when you do not have a time reversal invariance, you get a Z. So this is really the you have no time reversal invariance and so on and so forth. So you can look at one of these things. There is no time reversal invariance here, and there is charge conjugation here, and then there is no chiral symmetry. So probably this is the quantum Hall system, and if you look at this, it falls into the D class, and in 2D it should be the Z invariant, which is the Chern, which is called as a Chern number. Z is called as a Chern number, and Z2 is called as some Pfaffian or something.
It is called torsion,
Okay, okay.
and it cannot be written as an integral.
Z2.
Cannot be.
Okay, it is obtained from this.
Topology is-
Yeah, so originally that was calculated from the Pfaffian of a matrix, but there are other ways that we use where actually we use an integral by putting the path of the integration into small. There's a method that has come up in the last 4 or 5 years. Not discussed, but that's a very intricate method. That's a method by these two guys called Fu and Ken, Liang Fu and Charlie Ken. Yeah. You don't have an invariant. You don't have an invariant. It's always trivial. Okay, so coming back to this SSH model, you have this, the extreme dimer limit where there is no hopping between these two and so on. So the V is only there, there's no W, and there's only W is there. So these are the two limits. So V equal to W, that is V is the hopping between these two carbon, and W is the hopping between these two carbons. So V becomes equal to W, that's a gap closing line. So if you come from this point to this point, you don't do anything, they are adiabatically connected. And if you go from this point to this point, they are not adiabatically connected, and you have to undergo through the gap closing transition. So here you have a topological transition if you come from this white region to the shaded region. And the shaded region is trivial, where V is greater than W, where V is this hopping and W is this hopping. And this is possible to show in a very simple manner. If you write down the corresponding Hamiltonian in the form of a massless Dirac form, which is D dot sigma, sigma the Pauli matrices, and D is some some vector which depends on this K. And fortunately for this problem, this is a dx dy plane. So if you have these red circle encircling the origin, you have the topological insulator, and if it comes out of this, it's a trivial insulator, and this is kind of the gap closing point where the edge of the circle simply touches the this origin. And why it would be very difficult to define a topological insulator if you have Z also. So in this D dot sigma, you'll have one of the components missing. In this particular case, the dz component is missing, though sigma z is not there. Suppose you have this sigma z, then it's very difficult to do this characterization, because this red circle here can go out of the plane and become this red circle. So you don't know whether it has actually missed that, or this how this transition occurs. So luckily for this model, you have this dx sigma x and dx dy sigma y. And then what you can do is that you can calculate what is called as a winding number, which is again like a Z invariant, and this can be calculated like this. And for this, if V is less than W, this thing that we have shown here, if V is less than W, you have a topological state, which means that this is equal to 1. And if V is greater than W, then this is equal to 0. So the system undergoes a topological to trivial transition.
One should be greater than the other.
So that's the kind of critical thing, where V is equal to W. it should be one should be greater than the other. One should be greater than the other. At that point, everything becomes ill-defined. You can't calculate the Berry curvature and so on. That's the gap closing thing. And this is in a higher dimension, one actually needs to calculate the Chern number or the Z2 invariant and so on and so forth. So if you look at the band structure, now coming back to the open chain to the the periodic boundary condition, this is W equal to 0. One of the hopping is 0. This is V greater than W, which is the trivial case. This V equal to W, the gap closing case. Okay, V less than W, the topological case, and V equal to 0, the other dimer case. So if you look at this thing, the winding, you see that this winding is just a point outside the just a point here on the dx axis. Here it's an insulator. This is also an insulator, but the condition here is that V is greater than W. Here V is less than W. Here the circle, the dx dy, as you vary k, it doesn't involve this thing, or rather enclose the origin. This just touches the origin and this encloses the origin. So there is a topological insulator and there is a trivial insulator. So in going from a trivial to a topological, you have to go through the gap closing transition. This is exactly what I was saying earlier, that in unknotting a wave function from to a trivial wave function, you need to cut it open. You can't smoothly deform. If you could smoothly deform, then they would form into, or rather they would lie into the same topology class. And so these are some of the these things. I have 11:15. Okay, so these are some of the topological invariants. I mean this conduction and valence, etc. And there is a Chern insulator which has got one mode like this, and this another quantum spin Hall insulator. You need to calculate the Chern number or the Z2 invariant. It's not so basically that's the again the Berry curvature. The Berry curvature is here, and so on. And then the Chern number is calculated as the integral of the Berry curvature. This is like that Gauss-Bonnet theorem, the 2 pi into 2 minus g, and this is that integral. So let's not worry about 2 pi into 2 minus g. That's a mathematical thing. For us, what is important is the Chern number comes as the integral of the Berry curvature over the entire Brillouin zone. So let us go a little ahead. This is not so important. Yeah.
Experimentally, have they found situations where the G that you mentioned is more than 0 or 1?
Yeah. The Chern number, the plateaus.
Corresponding the neuroscience 2 minus 2G.
Uh-huh.
Have there been experimental situations where the
G
has been reduced to be greater than 1?
Yes. So the quantum Hall state is the G can take any value, any non-zero.
What I mean is, has it been clearly identified as G equal to 2 or 3 or something?
Yeah, so the Hall plateaus that you see are the, so this Gauss-Bonnet theorem, forget what was there, 2 pi into 2 minus g, just call it as C or K or something. So the values of C equal to 0, C equal to 1, C equal to 2, C equal to 3, C equal to 4, all values have been, have been found.
In particular,
Assigned to particular, absolutely. So I just take one short, this thing that, yes, exactly. Each one of them, correct.
And where will, for example,
Fractional will not. This is all non-interacting things, and interaction, when you need to invoke the interaction, you have a different sort of story altogether.
Is it kind of the material dependent?
Yes. I mean, material dependent means if you have a clean system, then these fractional things that appear, and then these one-to-one correspondence between this, because it can be easily shown that the Chern number or these invariants have an integer value. They can't have a fractional value. And these fractional values would only come from some materials where you need to consider additional things. I would sort of this is Z2 invariant is another thing that one considers, and there are the methods which are there. It's not important here. They calculate what called as Wannier charge centers by using these Wannier functions, and this was actually by Vanderbilt and co-workers. They have done that. And so these are some of these things that we do. These are the Berry phase is plotted as a function of one of the momentum in a 2D system, and if it cuts this thing by an odd number of times, then it's topologically non-trivial, and if it cuts even number of times, it's topologically trivial. This is how we calculate the Z2 invariant and the Z2 invariant is particularly relevant for whether the time reversal symmetry is valid. Okay.
When the SSH model, if you introduce interaction,
Huh.
will it mimic the
Yes, not fractional Hall, but there'll be some. If you do this, probably some MBL kind of thing can appear. Many body localization kind of thing can appear. So quickly going on to the non-Hermitian system, a lot of research that went on recently and so on, and some of the key properties of non-Hermitian systems is an exceptional points. And why they're called exceptional points? Because these the Hamiltonian becomes ill-defined. If you have degenerate eigenvalues for a given matrix, you still have the eigenvectors to be distinct, right, corresponding to those values. But here, the eigenvectors also become identical. So that is called as exceptional points. There are point gap and line gap. There are non-Hermitian skin effect, which is what you're saying. And then, of course, there's a new refined bulk boundary correspondence. So let's just quickly sort of see what are the exceptional points. If you write down a Hamiltonian, which is a diagonal one, say 2-component Hamiltonian, and this connected by some matrix, and if you calculate the eigenvalues, so then you'll see that the eigenvalues and the eigenvectors, they'll coalesce at particular values of lambda, and these are the particular values of lambda, and so on, and the eigenvalues become like this. So at the EPs, the eigenvalues, that is at these the lambda 1 and lambda 2, the eigenvalues will look like this, and the eigenvectors will look like, at lambda 1 it will look like this, and lambda 2 it will look like this. So they become kind of same. So that creates a problem. I mean, the kind of the Hamiltonian becomes ill-defined, and so these are the two exceptional points. There is another thing called as a point gap and a line gap. In a normal Hermitian model, you have these real eigenvalues, and they are on two sides of the Fermi or whatever. They're nicely separated by this Fermi point. In a non-Hermitian model with a point gap, if you plot the imaginary E and the real E, it will be distributed like this about a point. And in some other model, another non-Hermitian model, you can have these eigenvalues that are distributed like this about some line and not about some point. So these are called as line gap, and these are called as point gap. So both are there depending on what kind of non-Hermiticity you have. And non-Hermitian skin effect, again, this is like what happens is that in a non-Hermitian model and having topology, all the states are pushed at one end. And if you tune the parameters slightly, they are pushed at the other end. So this is, in a way, they have sort of tried to visualize it that as if it's like an information of quantum information transfer, because the chain length can be as large as you want. So from one end of the chain, it can be sent to another end of the chain by just simply tuning some parameters and so on. And so this is the non-Hermitian skin effect. You see that there is a buildup of the eigenstates at one edge and not on the other edge. So if it goes from here to here, it has to go through these entire thing being kind of the wave function is evenly distributed at all sides. So one quick way of looking at whether a model will have skin effect, you need to look at the imaginary versus real E spectrum. If they look different, then there's a skin effect. If they look same, then there's no skin effect. Okay, so you just plot the imaginary E and the real E. So what we can do is that this is slightly technical. It's called as a non-block theory. And the non-block theory, all know block theory where K is a real, variable, and something with translational invariance. You can write down the wave function as a block function and so on. Here K is not real because your energies are not real. So what you can do is that you can write this K as some real part and an imaginary part, and write down this quantity as some mod of beta. So beta equal to mod of R into exponential Ik, and you can plot the generalized Brillouin zone. So this imaginary beta versus real beta. Beta is here, and by solving this determinant, the characteristic equation to get this beta and some boundary conditions. So now you see that the Brillouin zone is not a nice and regular shaped object. Rather, it has cusps, and it is, in this case, it's greater than 1. In general, for a Hermitian case, it is just equal to 1. So it's that one circle, little n circle, and it's not like a cusp. So these are called as non-block theory. This was nicely actually wrote down by Bender, and in fact many of the high energy physics problems can be nicely solved. So if you look at the original system with these two hands, if you do a parity reversal, then you see that this the right hand is moving when the left hand is moving, and if you do a time reversal, that is first you move the right hand and then you move the left hand. So these two situations are different. But if you have both the symmetries, then this is exactly mimicking that. Okay, so this is called as a PT symmetry, parity time symmetry, a thing that is very extensively used in optics. And Bender actually wrote down a nice Hamiltonian with p square and minus ix whole to the power n. And this Hamiltonian will represent a harmonic oscillator if n is equal to 2, and it turns out that for n greater than 2, the spectrum is real and positive. So it's a non-Hermitian Hamiltonian, but still with real eigenvalues for n greater than 2. For n equal to 2 is the usual harmonic oscillator. For 1 less than n less than 2, between 1 and 2, n 1 and 2, in between that, the finite number of real and positive eigenvalues and infinite number of complex conjugate pairs. So this is between this, and at n equal to 1.42 exactly in this model, you have exactly one real eigenvalue here. Okay, for n less than 1, there are no real eigenvalues and the energy diverges. Okay, so that's a nice PT symmetric Hamiltonian. So it's still at tweaking the Hamiltonian in a given way, and what you need to understand is that all these known concepts of Hermitian systems now will have to go away because your H is not equal to H dagger. Okay, and because of that you have a right-handed thing. So this is the Hermitian definition of Berry phase, and the non-Hermitian definition is that this psi has to be replaced by a lambda, where lambda is the left eigenvector and psi is the right eigenvector, and they have to have this nice bi-orthogonality or bi-orthonormality conditions where the lambda and psi inner product will have to be equal to 10 minutes. Yeah, I'll do that. So this is that thing, and so these are some of the properties written, exceptional points, there's degeneracy and so on, spectral gap, bulk boundary correspondence. It fails generally, but if you take into account the non-block theory, it is fine. Then there's bi-orthonormality and so on and so forth. Let's come to the last point, which is periodically driven systems. So we have a driven system. So if the Hamiltonian is explicitly dependent on time, how we are going to solve for the system, because you have a time dependent problem. So fortunately, if it's periodically driven, then there is a formalism that exists, which is called as the Floquet formalism, and we get Floquet topological phases, and we get origin of the pi modes and so on. And these origin, I mean, these pi modes are related to quantum computation, which I don't show here, but that's important. So you have a Hamiltonian which has this periodicity. This Bloch's theorem says that these energies, now the Bloch's theorem is reformulated for energies where these quasi-energies are contained in this Floquet-Brillouin zone. Okay, so these are these Floquet-Brillouin zone. So there are these modes at minus h cross omega by 2 and plus h cross omega by 2. So your Floquet-Brillouin zone is between minus pi by t to plus pi by t. Just like your k was between minus pi by a to plus pi by a in a periodic system, your energy is now between minus pi by t, where t is the time period of driving. How does one solve it? A little bit of technicalities. This is called as a Shirley-Floquet approach. So the Hamiltonian, the effective Hamiltonian becomes this infinitely number of such things. But fortunately, for a harmonically driven system like V cos omega t, the only off-diagonal terms will survive. So it becomes a 3 by 3 matrix with m equal to 0 and plus minus 1. So you have this only this kind of the small matrix. Okay, so that you need to solve. And what happens is that the unperturbed bands, so the 0 modes and the pi modes, so the unperturbed bands look like this. There's a crossing, etc. there for no driving, and if you have driving, there are gaps that open up. Okay, so there are these gaps, and now you need to ascertain whether these gaps are trivial or these gaps are topological. Okay, so you need to look at the properties of the wave functions of that gap and calculate Berry curvature and so on and so forth. Okay, so these are called as pi modes. They are at pi by t and minus pi by t. These are called as pi modes. So this new addition to the field of topology came in the form of topological crystalline insulators. And so this was again a paper in 2011 by Liang Fu, who said that all these things are you need to include crystal symmetries. And so this tin telluride soon became predicted to be a member of the topological crystalline insulator. So this was a paper by this group, and they actually predicted there's a higher order topological insulator. So there was another paper in 2015 or 2015 by the same Liang Fu's group. And so there are conventional topological insulators. Then there are topological crystalline insulators that came in 2011. Then there are tin telluride in 2012 as a topological crystalline insulator. New class of 3D, this is a 3D crystalline insulator in 2015. And these are these higher order topological insulators, which are subclass of topological crystalline insulators in 2018. So we have these higher order insulators, which have now, instead of d minus 1 dimensional conducting modes, you have d minus 2 dimensional conducting modes. So if you have a system in 2D, you'll have 0 dimensional conducting modes, which are like at the corners, and there are hinge modes at this, at these things and so on. These HOTI, as they're called as higher order topological insulators, is a subclass of these topological crystalline insulators. And this was one of the first, other than tin telluride, this is the bismuth was always known to be a kind of weak insulator. So there is a little bit of, gap at the Fermi level here. But when you look at the band structure carefully, you see along this line, there are the inversion symmetries change values twice from a minus to plus. Because of this two changing of values, there are two band inversion, and that made bismuth to be a higher order topology. Similarly, bismuth halide chains became higher order topological insulators with two, these kind of inversion symmetry breaking transitions. SNT. Then there was a lot of theoretical work where actually they wanted to change the sign of the Dirac mass across a hinge, and that gave rise to this, the Dirac cones. Actually, they open up masses in going from this to this. So there is a gap, closing transition here, and you have helical edge states. Then the Schindler's group, they have done some theoretical calculation on that. So this is that the crystalline term. If you have delta 2 not equal to 0, then there are these hinge modes. Otherwise, in absence of that, there are surface modes that are there. So in absence of delta 2 equal to 0, you have so in delta 2 equal to 0, you have a normal first order insulator, which we have been talking about. With delta 2 not equal to 0, you'll have this. This is a paper by Diptiman Sen's group, which they have exactly done this 3D thing to 2D, and they have got these corner modes and so on. And so if you look at this is a topological insulator. This is like a trivial insulator because at the Fermi level there is a gap, but it's not a trivial insulator. It's a higher order topological insulator with all these things. So having said all that, and I have about 5 minutes. Okay. I'll just quickly show that some of the calculation that we have done for the ladder, and stop there. And this ladder is a compound. Why we have chosen this is that it lies between 1 and 2D. So the standard classification should not work. It's a nice system with some horizontal hopping, and some vertical hopping and some diagonal hopping. And this ladder, so these are the ladder sides, and there is a flux that comes towards you because of these are the hoppings are kind of this picks up a phase. And if you solve this model, this was written by Cruz in 99, and then you have this so there is a for R to be equal to 2, there is no topology here. For R to be less than 2, you'll have these 0 modes that are there. That's precisely the topology of this Cruz ladder, and this is all shown here. So we have, so if R is less than 2, you have the wave function completely distributed all across the ladder. And if you have R to be less than 1, there is a buildup of the wave function at the edges showing topology at R equal to 0. So if you shut down this hopping, then you have this complete, the complete localization. So if you do a driving of the ladder kind of thing that we were talking about, then you have these same formalism. And so this is no driving. You have 3 replica of this in the Floquet formalism. There is a gap closing here, there's a gap closing here, there's also a gap closing here and here. So if you use a frequency, okay, so this is the TV not equal to 2TD. We have changed the sign somewhere. We have changed this notion somewhere. So now this is called as TV, this is called as TD diagonal, and this is called TH instead of LR and so on. So this is so now in this particular case where you have TV equal to 2TD, which is R equal to 2, and you are driving the system, you have gaps that open up. So you need to understand whether these gaps and these gaps, they are topological and trivial, and that's what happens. And so both the 0 and the pi energy gaps, because now there are not only 0 energy gap, there are pi energy gaps as well, which makes the system richer in terms of topology. And these are shown. So this is something interesting because you should not have a topology here, but in presence of driving, you have a 0 energy mode here. Okay, and so topology is getting enhanced. And so there's a non-Hermitian version as well, where we have put a staggered mass term and have calculated the Brillouin zone using the non-block theory. You see there are these pi modes here, and the 0 modes here, which are shown by what are these, the Chern number or the topological invariants, and these are the non-Hermitian skin effect that happens, and these are the corresponding, the Brillouin zone using non-block theory, and so on, and these are precisely saying the same thing. Finally, just one or two slides on this higher order topology, something that Manideep is doing. So we have stacked two truths ladder, one in the x direction, one in the y direction. And by doing that, you get higher order states. If you look at this probability distribution, which are shown here, you have, instead of these edge modes are gapped out and giving rise to the corner mode. So that's a higher order topology here. And similarly, you get higher order topology in other parameter values as well. And finally, just to summarize, so we have topology. We have discussed topology and tweaking of topological matter, and the effects of non-hermeticity, periodic driving, inclusion of crystalline symmetries in the form of higher order topological insulators, and finally, I've applied it to truths ladder. Some of the publications, in this along these lines, some more in the last 2-3 years. So these are some of the publications, and these are the workforce that have done all the hard work. And so these are PhD students. He's a postdoc. And some undergraduate students, very bright undergraduate students from IISER Kolkata, our own students, these two. And this is a student at Shivnadar University who works on this fault-tolerant computations and so on. And that's a few things about our campus. It's extremely beautiful. That's a lake that's there in the middle, and there's night photograph. Thank you.
Very good. So I think it's a very
We finished on time.
We exactly finished.
Exactly.
Time, but we should have also. Okay, now I'll go to the back bench. Benches.
Oh, hi.
So this is really
Good to see
quantum
you.
questions from quantum mechanics. So you should have some questions from here. Yeah. So all you have learned from the Hermitian matrix. He was talking non-Hermitian matrix. Ask why the eigenvectors are not real and where are the systems. I just showed you where they only appear. No.
There's a question here.
Okay. So after that. Okay. After that. At least somebody should ask.
I'll help them out.
I know you. No. Mass of the electron of
There's no question. He's asking.
9.1 into 10 is to power minus 31 kilogram.
Okay. Almost
Yeah. Okay. Maybe. Go ahead.
Yeah. So about this higher order DI, higher order, do you mean higher order of the holding is higher order, or
No. Higher order means in a two-dimensional system, you have one-dimensional edge modes. So it's d minus 1 in a standard topological definition. Higher order means it's not d minus 1, but it's d minus 2 kind of modes, which are conducting modes.
but there is a crossing that is still fourfold. They are still
Which crossing you're talking about?
there is any
Energy.
structure, if there is they still reflect DI.
If there is a crossing, that's a closed gap scenario. So after that, the gap opens, then you have to ascertain whether the gap is topological or trivial.
But the situation when there is a crossing, like in topological insulators, they are fourfold, right? Go from TI to say Y, it splits and becomes 2 to 4.
Okay.
In the band structure concept, there are still crossings that you may have.
Yeah.
Of higher order system.
In the band structure, you can, there shouldn't be crossing. There should be gaps open up. But why? So there has to be two band inversion, double band inversion that has to happen. Now, what is meant by band inversion? So basically, the property of the conduction band becomes same as that of a valence band. And how do you understand that? You can calculate the inversion matrix and eigenvalues of the inversion matrix, and then you go across the Brillouin zone like a gamma point to a K point to an M point and see where that inversion thing.
Do they need any specific symmetries?
So good question. That
Unlike normal PI.
So that's the best question, in the sense that you have to embed somehow the crystalline symmetry, which was not taken care in the normal topological insulator. They only take care of the discrete symmetries like time inversion, time reversal and charge conjugation and all that. Here you need to somehow embed the crystalline symmetries, and then there'll be an additional gap closing where your edge modes will get gapped out and they will have to appear somewhere at the corners. Correct, exactly. In fact, our thing's also similar. So you don't understand by looking at the band structure. You have to calculate an appropriate invariant in order to understand that. Correct, right. They haven't done that in that paper. Later on, this we haven't done. We have calculated a 2D winding number for each one of the Creutz's ladder and along the X and along the Y. But we were talking to Nabendu yesterday that there has to be a nice, characterization of this higher order topological phase in terms of the bulk boundary correspondence. So you need to have a bulk invariant which would characterize this even though your band structure has a gap. So it will look like a normal insulator, but it's not. It's a higher order insulator.
In some cases, if you follow that tenfold OS,
Yeah.
then that standard topological number is 0.
Yeah, exactly. The standard topological, you have to find a number. Everywhere we have faced that there's a challenge in finding the number. There's a unique challenge every time. He's facing the same thing at this point. Yeah.
So I want to probe this non-hermeticity a little bit further. So,
Yeah.
So if you have an e to the plus power of IMT and e to the power of minus IMT time dependence, and you let those m's, do their thing, then in principle you can get some non-hermeticity just from there, right?
Yeah.
But so are you saying that there is some non-hermeticity above and beyond that, or the non-hermeticity is captured by that?
Okay. Exponential I omega and minus I omega. A good question. See, non-hermeticity in our kind of model can arise in two different ways. One is what you can put in sort of complex terms at each of your lattice sites or points, and this is actually a sort of case for PT symmetric Hamiltonian. Okay, and there is no, in general, there is no skin effect that we talked about. In another kind of Hamiltonian, which you make the left-right hopping to be distinct from the right-left hopping, that is where what you do is that if it is, say, one is greater than the other, you push the wave functions to either this edge or that edge, depending on which one, the right-left hopping or the left-right hopping. So in both ways, and this is actually a PT sort of broken system. Okay, so in both ways you can do that. The ramifications are different.
Can I make a remark on this non-Hermitian models? The Hamiltonian formally has a set of eigenvectors.
Yeah.
Presumably infinite number of them.
Yeah.
So you declare a new scalar product saying that any two of them linearly depend on half other.
Yes.
That changes the scalar product, but in the new scalar product, the original Hamiltonian is self-adjoint. That's the problem. So it's a change in the scalar product that is creating this situation. If you change the scalar product like that, this volume form you are getting is not Lorentz invariant.
Correct.
So
Correct.
I do not know how to carry it over to a quantum field theory which is Lorentz invariant.
Correct. I do not have an ready answer for this, but this is something that we have faced from the referees. So what we get by in most of the cases, by taking the eigenvectors of H and taking the eigenvectors of H dagger. And whenever we have to calculate an expectation value, we use the left for the H dagger and the right for the H, and we get by doing that. But I really have no concrete answer that why that should work and so on. So
Let me conjecture. Let me conjecture. So, look, I mean, what's happening is that you have these two different surfaces, right?
yeah,
The left surface and the right surface.
correct.
Now, the left surface and the right surface have actually different. I mean, on one of them, time actually moves in the positive direction. If you want to think about it that
Are you
way.
talking about the real space of the system?
No, so for your no, not. I mean, I'm talking about doing the time evolution for the left and the right modes separately. If you do the time
Okay,
evolution
okay,
for the
okay.
left modes and the right modes separately,
Okay.
then you can actually get the eigenvalues for the Hamiltonian of one sign for this and for the opposite sign for that. And if you do this in separation clearly, then problems will go away. That's the point.
Sachin.
Yeah, so I think because this non-homogeneity is so puzzling.
Yeah.
I also want to ask you something. Okay, until the discussion of these kinds of topological insulators, both experimentalists and theorists were, especially the theorists who talk to experimentalists, were content to work with Hermitian Hamiltonians.
Correct.
Even though in real life there is coupling to the environment and there is dissipation.
Correct.
Because the experimental time scale was much faster compared to the dissipation time scale.
Yes.
So
Yeah.
Hermitian Hamiltonian was an excellent model
Correct.
for the underlying experimental
Correct.
setup.
Correct.
What is new in the experimental situations that people are creating that you need to switch to working with dissipative Hamiltonians? Is the dissipation so fast that even on an experimental time scale you are losing probability conservation?
That's a fantastic question. In fact, this is what if you look at an experimental setup that they have designed, this is there in the web, and it's some Europhysics letters, which is not a very well-rated journal, but they have this feature article that actually you can do experiments in the time scale where the non-hermeticity or coupling to the environment has to be taken into account. It's an optics experiment clearly stating the kind of Hamiltonian that I wrote, a 2x2 Hamiltonian. So there are two sort of cavities, and these two cavities are coupled by some link, the same 2x2 Hamiltonian and so on. And they actually shown by doing experiments that there is a need to take into account the dissipation, which you cannot get good answers.
So that will be one experiment where the dissipation is
Yeah.
really fast,
Yeah.
and you need to maybe a non-Hermitian. But from what you described in this business of topological insulators, there is people are using non-Hermitian Hamiltonians a lot.
Yeah.
Not just in the example.
Yeah.
In those situations, is the dissipation like this, that it is so fast compared to the time scale over which you are doing the experiment? You need to worry about the probability leaking of probability.
But this, even by us, we have actually made circuits, electrical circuits, made out of capacitance, inductance, and diodes. These diodes have a new name called INIC. Whatever. I mean, it does the same thing as a diode. And we have actually looked at, in a non-Hermitian model, there is generation of non-Hermitian skin effect, which means in such a circuit, if I calculate the impedance between 2 points, then I see that there is a large impedance if there is a non-Hermitian skin effect, or there is this topological things that is there, and there is nothing otherwise. So the non-Hermitian skin effect can be probed, but the time scales that you talk about, I am not too sure. I mean, which is not.
Maybe I'll ask you.
Yeah.
These eigenvalues are all real.
Yeah.
If the Hamiltonian can be exponentiated to exponential AHT,
Yeah.
so there are issues of
Yeah.
then evolution will look irritating. in this, because this eigenvector you are giving span a vector space, on that it will be a unitary evolution with a new scalar product.
Yes,
So
yes.
there will be no dissipation.
Yes. So in the PT symmetric case,
That's
so
why I want to come at it from the experimental side.
so in the PT symmetric case, in a restricted sense, you have all the eigenvalues to be real. Okay, but as you change, parameters, etc., you'll have these non, these imaginary eigenvalues they appear.
I think the only experiment I have seen is in optics.
Yeah.
Which are not quantum mechanical, they are optical experiments.
Yes,
I know
but
they are not quantum. But
Okay.
they are just classical.
classical.
Now,
Okay. Okay.
one more remark. You talked about level crossing. That is, suddenly the degeneracy is only one at some levels.
Yeah.
This is quite familiar to people doing, for example, Sachin Iyer. So suppose you have a chirosymmetry break
Yeah.
by instance.
Yeah.
Then the zero modes of the Dirac operator in the break broken phase, the left and the right modes do not match.
Okay. Okay.
Now, break this symmetry by hand by putting a some term which has no chirosymmetry.
Okay.
Then the excited levels will be paired.
Okay,
Because of-
yeah.
Exactly paired. But now gradually switch off the interaction.
Okay.
You are putting, it will go down to the zero modes, but then you will find that they are not doing the smooth thing.
Okay. Okay.
So there
Okay.
are many examples of this kind in quantum field theory.
Quantum field theory.
I
Okay.
don't know why it is so. Why there is this first
So
emergence here.
I think it's a quite high time, so high energy people should jump into the condensator and provide the suitable language.
No, in the context of topology, this becomes an important.
No, this,
Again, I have problems with the use of topology. Topology is giving a set of open sets.
Yes, I'm not using in the mathematical sense, but more like a, yeah.
no, anyhow, sort of related to this thing, since you have PT symmetric Hamilton, which has only real eigenvalues.
Yeah.
Essentially, you can go by a similarity transformation, not a unitary transformation, to a problem which is completely unitary and
Okay.
this thing.
Okay.
Where if you want to compare with this thing, you have, as you were saying, the dual space versus the space, and then you are comparing, which essentially means what happens in say forward direction in one side will become negative direction in time in the other one.
Okay.
And if you have a way of describing that the system in such a way, there is dissipation on one side and there is something else coming in.
I mean,
whole
being
thing-
fed in. Yeah.
being fed. So
Yeah,
that the
yeah.
whole thing will become completely unitary.
Yeah.
And
Yeah.
then you can take subset of that the way you
Okay.
want.
Okay.
And
Yeah.
take
I
it-
mean, in a restricted sense, this could be achieved actually experimentally. Yes, I agree with that. Yes, I agree. Yeah, I agree with that. Yeah. Thank you.
Very late.